Okay, so I really would like to thank Avner and Jim for giving me a chance to present the paper. This is co-authored with Shaojin Li, who is stuck in Shanghai teaching, and with my student Yufeng Wu, who is off giving a job talk somewhere, and so you're stuck with me. So we're asking a question. So how much do taxes matter for leverage? And this is, of course, an extremely old question, but I think still a relatively unsettled question. And we're interested in this question quantitatively and relative to frictions related to the preservation of debt capacity. So this is a super hard question. It's hard to find exogenous tax changes. They don't happen in vacuums. And these frictions that are related to the preservation of debt capacity are unobservable. So if you want to ask this question empirically, there are some serious data limitations. So we're going to take the easy way out, and we're going to estimate the parameters of an optimal dynamic contracting model. And the contracting friction that we're going to think about is limited entrepreneurial commitment, i.e. the firm can take at least part of the capital and run or give it back or forfeit it as collateral. On top of this, which is a very standard framework, we're going to layer on taxation of corporate income with what's going to look a lot like an interest tax deduction. And we get some really interesting results. The model with taxes fits the data exactly as well as the model without taxes. When we do counterfactual exercises to see if taxes matter for leverage, they largely don't. The model, and we try to see if the model actually has some external validity, and it appears to be very good at detecting the change in collateral from a natural experiment that involves collateral values and repossession. And then one last very nice result is that because we have a model, we can quantify the value of preserving debt capacity and the value of preserving financial flexibility. That's the cost of leverage, or losing that is the cost of leverage. It turns out that's exactly equal to the tax benefit. So there is no horse and rabbit stew. There's a horse and rabbit stew if you compare the tax benefit to financial distress costs, which are both low probability and remote. But if you compare the tax benefit to a cost that is everyday here and now, they're about the same. So how did we get to that? Well, before I can explain the intuition, I have to talk a bit about the model. I'm going to talk about the technology, the contracting problem, how we introduce taxes, and then some optimal policies. So it's discrete time, infinite horizon. And this part's very standard. The firm uses capital to produce output. So output's Y. 1 minus tau C is after taxes. Z is a shock to the production function, which is decreasing to returns. K is capital to the alpha. Alpha is less than 1. Z is a stochastic shock. It has a transition matrix. And because the firm has capital, it invests in capital. And so tomorrow's capital, KT plus 1, is equal to the depreciated value of today's capital plus investment. And we have no adjustment costs. Later I'll put in adjustment costs. For now, it's easier without them. So when the firm starts out, it's small relative to some sort of notion of an optimal size. And so it needs financing. It enters into a contract with an intermediary. We're going to assume for now, we'll relax this later, that firms have lower discount factors than these intermediaries, i.e. they are more impatient. Lenders are more patient. There are a variety of reasons that you might imagine this to be true. So for example, insured deposits would do that for you. So this simple little institutional friction. The firm can, so here's now the contracting friction. The firm can renege on the contract, but it's a one-sided limited commitment setting, so the lender commits to the contract. So what is the contract? It's a state contingent triple. So I is investment, D is dividends, P is payments to the lender, and the goal of the contract is to maximize the firm's equity value subject to some constraints. So the first one's a little controversial. This is limited liability. That says that dividends have to be 0. So relative to some of my earlier work, which allowed for negative dividends, we're just going to get rid of that. If you think about this from an empirical standpoint, it's not that big a deal. Seasoned equity offerings happen, once every 20 years? And on average, they're about worth, 0.1% of a firm's assets. So if I can't explain something that's about 0.1% of a firm's assets, I'm happy with that. Then we have a budget constraint. That just says that the sources and uses of funds are equal. And then the enforcement constraint. So to explain the enforcement constraint, I have to tell you what happens when the firm reneges. And if it reneges, it gets to keep a fraction 1 minus theta of the capital. And then its liability is set to 0. So it gets a punishment. It has to, in some sense, forfeit some of the capital to the lender, but then it gets a benefit. It doesn't have any more debt. At this point, we're going to diverge from much of the macro literature and not assume autarky. They can go back into the market. They can be Continental Airlines. And they can continue operations. So what's the value to the firm of reneging on the contract? It's just the alternative dividend stream when it gives up some of its capital and gets rid of all its debt. And that's what that D hat is. That's the dividend stream when you start off smaller, but you don't have any debt. Okay. Now, what's going to keep the firm from reneging? Because in the contract the lender commits, the lender would never want to enter into the contract if it thought that the firm would renege. So we need this enforcement constraint, which just says that the value of playing by the rules is bigger than the value if you don't play by the rules. So the value from continuing the contract, that's the standard old dividend stream, is greater than the repudiation value, which is greater than this alternative dividend stream. And if that holds, the contract's self-enforcing, because the firm would never want to renege. So it's actually pretty simple at this point. And the contracting problem is very intuitive, but it's a little intractable. We're going to maximize equity value. That's the first line. Subject to some constraints. There's limited liability. There's the budget constraint. There's the enforcement constraint. And there's a lender's initial participation constraint that says that they at least get their money back initially. Okay, so that's intractable, but you can make it tractable. And so we're going to do a very standard trick in this literature and recast it recursively. And so we're going to define this thing Q, which is not Tobin's Q. It's actually the present discounted value of payments to the lender. So it's, in some sense, some sort of market value of liabilities. And then you can recast this as a Bellman equation. So the value of the firm, that whole top line is just the profit flow. So we've got the first term is profits, second two terms are investment, and then the third term is just, you can back that out of the top line, payments to the lender, plus the continuation value. And so now this is tractable, that's sort of, subject to limited liability and enforcement. And then we're going to do one more trick, which is from the Rampini and Viswanathan's work, which is this enforcement constraint. The value, if you play by the rules, is bigger than the value if you don't play by the rules. Gives you the same set as this collateral constraint, which says that debt is less than or equal to the collateralizable value of capital. And of course, they won't renege if their debt is collateralized because they can't. Okay, so that's the model. Now, we're going to add some taxation in. And this is a little bit tricky because these state contingent payments to the lender really aren't split up into principal and interest. And so I'm going to put on something that looks like an awful lot like an interest tax deduction. So we're going to assume the firm receives a rebate from the tax authority that's Q, that's the tax base, times tau C, that's the tax rate. And then that 1 minus beta C business is roughly an interest rate, right? For small interest rates. And so that looks an awful lot like like an interest tax deduction. Couple things to note here. It's pretty easy to map this back into the original sequential problem. It's just more convenient to start it here. And two, we're not going to favor any specific form of payment to the lender. They all get the same rebate. And then we get this. And obviously, I want you to look at the purple and the blue stuff. So look at the purple stuff first. What does taxation do? It changes the firm, it makes the firm effectively more impatient. It changes the discount rate. That's the purple. And it also makes the benefit in default a little bit less. So when there's a default, the firm gives up its debt. But because it's getting this rebate, debt is not so onerous. And so the benefit of giving up the debt is less. It turns out that neither of these effects is very big quantitatively at all. And here's the intuition. That is a graph of the first order conditions for optimal leverage in a simplified version of the model. So on the horizontal axis, we have different debts, and on the vertical axis, we have the marginal benefits and marginal costs. So the marginal cost is 1 plus mu prime. Mu prime is the Lagrange multiplier on the future limited liability constraint. And debt is costly because you might end up bumping into that thing. And it's pretty straightforward to show that it's convex. It is convex. And then we have some marginal benefits, which are a function of two things, the tax rate and this lender's discount factor. So it is convex. And so let's look at marginal benefit 1. That tax rate is just barely above 0. And so at that case, we'll end up with a very low Q prime. If the tax rate goes up a little bit to tau C2, we get a huge increase in leverage. But when we go from 2 to 3, because of the convexity, we get a small effect. And so if there's a lot of convexity there, if there's a lot of curvature, taxes might not matter a lot. Now, I just drew this with graphing software, so it's not, it's a quantitative question as to how big that curvature is. And we'll address that in just a bit. The other thing to notice here is that beta C can change the level of that curve. So if beta C has already moved that marginal benefit curve up, taxes might not matter. The other thing to notice is that what might matter more is not the level of taxation, but where the curvature starts. If you compare this, where you have low optimal leverage, to that, high optimal leverage, it's really where the curvature starts and where the limited liability constraint might start to bind that matters more than taxation. Okay, but this was all, this is just speculation. We know it's convex, we don't know how convex it is, so we're going to estimate the model. And the first thing we have to do is measure debt. And debt is this present discounted value of state contingent payments to the lender. One thing that's true in the model is the lender doesn't own the firm. So what kind of liability can we exclude as equity? And then we're going to put everything back in. One question you might ask at this point is, but wait, debt isn't state contingent, but it is. There's this stuff called floating rate debt that's fairly state contingent. There are also performance sensitive debt. There are covenants which make debt state contingent. And so I think that it's reasonable to say that state contingent payments can be empirically measured as all liabilities that aren't equity, including leases. We're going to estimate beta directly, and for the rest of the parameters, I'm going to use SMM. You will note I have only 6 parameters. This is not one of those 27 parameter models. So I've only got 6 parameters to estimate, and I'm going to try to match 12 moments. So what 12 moments am I going to match? Well, what can the model say something about? The model can say something about debt, it can say something about investment, profits, and distributions. And we're going to try to match the mean, standard deviation, and serial correlation of those 4 variables. That's it. So we've got 12 moments. One thing to note here is we have 2 models, one where the tax rate is set to 0, one where it's set to 0.2, I think. And the results are nearly identical. The only one that's statistically, the only case in which the simulated moment is different in the tax and the no tax model is average investment. And that makes sense. Taxation affects the marginal product of capital. You kind of hope that would be different. But everything else, not statistically different. Very few moments are statistically different from their data counterparts. So if the 1, 2, 3, 4, 5, just 6, so not too many. And even fewer are economically different. So you'll notice that average actual leverage is statistically different from simulated leverage, but come on, 0.29 versus 0.3. There's only one moment that's both statistically and economically different, and that is the standard deviation of dividends. These are terrible models of dividends. So I wouldn't use this for a dividend paper. Don't worry, Kos. And the parameter estimates are not that different across the 2 cases. So the depreciation rate's a little bit different, the serial correlation parameter's a little bit different. They're almost all significant. It doesn't matter that much. So what's the intuition? The intuition is these firms are at an interior optimum, largely, but they're at a part where there's a lot of curvature. And so taxation matters, but it doesn't matter that much. one way to interpret what those parameters mean is to look at the policy functions for the optimal solution of the model. And the policy functions just tell you, if you're here with some amount of net wealth and some shock, what are your optimal policies? So on the horizontal axis, I have net wealth, which is roughly capital minus debt, and they're fungible, so I can condense them into one. And then on the vertical axis, I have lots of stuff. This plot is just a slice of the policy function for a given certain current shock. So what have we got? Look at the black line first. That's optimal capital. When the firm has low net wealth, it just wants to grow. Just invest as much as it can. However, at some point, it hits some bliss point where the marginal product of capital equals the user's cost, and it stops. When it's growing, it doesn't pay dividends. That's the purple line. But once it reaches the bliss point, i.e. is mature, then it starts paying out. And then we have state contingent debt, which is contingent on a low future shock, medium future shock, and a high future shock. And you'll see that when the firm has very low net wealth, the collateral constraint binds. The black capital line and the debt lines are proportional. But when net wealth gets higher, they only sometimes bump up against the collateral constraint. And the intuition is, if you're going to have a good future shock and good future investment opportunities, you want to conserve your debt capacity. And so, and it can go negative. And so very often in this model, the firms are not just always hugging the collateral constraint. They get to an interior optimum. So that's the policy function with no taxes. Watch the horizontal axis. The policy functions with taxes look almost the same, but the only thing really that changes, the scale of the firm went down. And of course that makes sense because when you tax the firm, the marginal product of capital goes down, and so they just operate on a lower scale. But everything else is the same. And once again, the intuition is that marginal benefit, marginal cost picture, where taxes matter, but not very much. And those two pictures are not identical, but they're awfully close. Okay, let's take the model and put it up to a little bit of a higher standard. I estimated on one sample of firms. Let's see how it can do on 24 from different industries. And so these are asset pricing pictures. They're like pricing error pictures that you've seen many, many times. So on all of the horizontal axes are actual moments, and on all of the vertical axes are simulated moments. The model does an awesome job with average leverage across these 24 industries. It does quite a decent job with profits and distributions. It screws up investment for two industries. Those are one of the mining industries and oil extraction, which are both wildly capital intensive. So the model doesn't do so great on those. But, you know, two, I'm okay with that. The other thing we can look at by estimating the model on a variety of different industries is we can look at the extent to which firms preserve debt capacity. So what I've plotted here is the collateral constraint versus average leverage. And they're not bumping up against the collateral constraint. They are preserving more or less, depending on the industry, debt capacity. And the ones that are preserving the most debt capacity are the ones that have more uncertainty. So in the industries where we have estimates of the productivity shocks that are very high, those are the ones that are conserving the most debt capacity. And that also makes sense intuitively. Okay. We're going to put the model to even higher test. We're going to test it on a natural experiment on the value of collateral. And what we're going to look at is secured lending through a special purpose vehicle. So these are just wholly owned subsidiaries whose sole purpose is to own collateral. That's all they do. So what does the firm do when it takes out a secured loan? It sells, It sells the collateral to the SPV. And then what that means is that the SPV is exempt from the automatic stay in bankruptcy, which makes it easier for the lender to repossess the collateral. Unless judges have seen fit to recharacterize the sale as a loan. If they recharacterize the sale as a loan, then in bankruptcy, the collateral goes back to the firm, it's subject to the automatic stay, and then the lender has a lot of uncertainty about the ultimate value of the collateral because who knows, the firm might fritter it away. Hard to know. So some states passed these things called anti-recharacterization laws. There was Texas and Louisiana in '97 and Alabama in 2001, and then a few more later on, which we are not going to look at. We're going to just focus on these. And one thing that's interesting about these laws is we researched who did the lobbying. And it wasn't the firms, it wasn't the banks, it was the securitization industry. And so yes, there are political economy considerations revolving around this natural experiment, but they don't really affect the players that we're interested in. And then there's this important court case, nullified them. This court case has been cited many, many times after. It's in many other court cases. So it's an important one. Reeves Brokerage versus Sunbelt Fruit and Vegetables. The judge ignored the Texas statute, he applied federal law, he recharacterized the collateral, and poof. So this, of course, lends itself to a diff and diff, except it's sort of an on-off diff and diff as opposed to a before-after. So on is after the law was passed, but before 2004, and treated as incorporated in these 3 states. And so we just do a standard diff and diff. And if you look at the top, those are the diff and diff effects. It's 0.072 if we don't put any other controls in. If we put controls in the forms of fixed effects or other variables, or both fixed effects and other variables, it goes down to about 0.04, but it's still highly significant, which is astonishing because we've only got about 200 treated observations. One always worries about common trends in diff and diff analyses, so we plot what's going on, and it's just obvious. So blue is treated leverage, red is control leverage, and you can just see the hump, it's there. It goes up, it goes over, and down. And so I don't think we're really picking up any sort of violation of the parallel trends assumption here. Well, we can do a diff and diff using the model. So we can estimate the model on control off, control on, treated off, treated on, and we can do a diff and diff on the collateral parameter, and it's about the same, which I thought was quite nice, because the collateral parameter is by no means the most or the only parameter that matters for leverage in this model. Leverage is determined by a variety of things. How variable the firm's investment policy is, which is determined by the firm's technology, and certainly by the amount of uncertainty it faces. But it looks like the model is picking up what is plausibly a plausible change in the value of collateral. How am I doing on time? Oh, I'm perfect. Okay, this is perfect. So let's move on to our counterfactuals. This takes a little explaining because I don't like 3D pictures. So this is a 2-dimensional counterfactual. We're going to start with a model that has no taxes in it, and we're going to take 2 parameters and vary them. So we're going to take 20 different values of the tax rate, 20 different values of the difference between the lender's and the borrower's discount factors. And then we get 400 different combinations, and we're going to plot those. And I just really despise 3-dimensional graphs, so we're going to get level curves here. The bottom level curve, the blue one, is for lenders and borrowers' discount factors that are nearly identical, and then so forth and so on until we get to black. And here we have the tax rate, up there we have leverage. And so what we have here is when lenders and borrowers are approximately patient, you do see an effect of taxes on leverage. But it's more pronounced for low tax rates than high tax rates, which is exactly what you would expect if the cost of borrowing is convex. If you increase the difference between lenders and borrowers' discount factors even just a little bit, like 0.01, that's not that much, the effect of taxes is 0. And that's where because at that point we're up in the very convex region and taxes just don't matter that much anymore. We get the exact same, so you might think that this had to do with the fact that taxes affect the marginal product of capital. You get the exact same picture if you just look at the tax deduction separately. So that's not what's going on. And this result is wildly robust. We have tried convex corporate taxes, dividend taxes, lumpy investment, costly equity issuance, and both of the Hennessy-Whited models. And we get the exact same result, counterfactuals. They're identical. get the same thing. And then the last thing I want to talk about is what's the value of preserving debt capacity? So we can do this in the model. So what we do is we calculate the value of the firm in the model with taxes. And in that model, firms spend a lot of time very far away from the collateral constraint. And then we just estimate we solve an alternate model in which we just force them to be up against the collateral constraint all the time. And then we compare the values. And that has got to be the value of preserving debt capacity. And it's about 7.8% of assets. And then we do a standard MBA textbook calculation of the value of the tax benefit, and depending on the tax rate you use, between 20 and 35%, it's about 5 to 10% of assets. And so they're the same. There's no, roughly, and of course we didn't match this moment. It's roughly the same. And so there really is no horse and rabbit stew. This value of preserving financial flexibility is a large force that matters for firms' capital structures. So I'm done. We estimated this dynamic contracting model, which was fun. But we did it because we were interested in a question, and which matters more quantitatively for leverage, collateral or taxes? And collateral matters a lot. It looks like taxes don't matter much. If you look at the empirical literature, with the exception of a couple of recent studies, by and large, nobody can find an effect of taxes on leverage, either internationally or in the US or anywhere. So it goes along with that, and it also is in accord with this paper by Graham, Leary, and Roberts, where they looked at the long-run leverage in the US from the beginning of the 20th century until now. And corporate tax rates in the US went up during World War II. And leverage went up over the course of the 20th century too, but the big hike up was 10 years after that big tax increase. So something caused leverage to go up later on, but not likely the tax increases from World War II. And that's it.